Hello, how's everybody doing today?
Going good.
Yay. All right. How is everybody doing? Fine. It's our last day of official class, right? Then we just have our final exams. So, and I know I sent you some surface area and volume videos of me just doing problems, which I thought might be helpful to you. I hope it was. I was thinking we could do one problem for practice. If you guys want. I was just trying to find a good one. Sorry, hold on. I was just calculating this. I put to the sixth power instead of to the second power. That's going to make a little bit of a difference, just in case you're wondering. So McKenna asked why we don't have class tomorrow. Does anybody know why we don't have class tomorrow?
You'll be out of town.
Very nice. Anybody know why I'm going out of town?
Your son's graduation?
Yay! Yes, my son's graduating from college in Omaha, Nebraska. So I am going to see, remember our semester was supposed to end already. So I would be finishing my oral finals today and I would be off to Nebraska with nothing on my plate to come home to. Unfortunately, we have extra time because of our lovely technology issue that we had. So, but it's okay. We made the adjustment and I did do a final already this morning. I have some more this afternoon. But most of you are next week, right? Some of you are like, oh man, I should have been today. And then others of you are like, are you kidding me? What lunatic is doing it today? Right? Yeah, some of you are thinking that. So it's okay. To each his own. We have different things going on. So, okay. Nice. Now we're done. I think. Okay. So today, so did you guys want to do a surface area or a volume problem, or do you feel confident in them? Speak up. It doesn't matter to me if we do one or not. You want to do one? Well, if we're going to do volume, we might as well do surface area. Surface area is actually harder than volume, believe it or not. So let me see if I can find you a picture. See if I can put this right here and share my screen. All right, 1 second. I did join with my iPad, thank goodness, today, so we don't have that to worry about. Okay. Oh, more helped a lot. Excellent. Okay, that was Vanessa who said that, just in case you thought it was me. It was not me who said that. It was Vanessa who said that. All right, so let's go first to our class. Okay, I just added this page, and we'll do surface area and volume of this shape. So okay. So there's no units on here, but we're going to say that these units are centimeters because I just arbitrarily decided that. Okay. Okay. So first of all, what shape is this?
I don't think you're
sharing.
Oh, you're right. I'm not, but I'm watching it greatly and having a great time watching my own screen. Thank you. You'd think on the last day I could have been on top of that, right? Nope, not going to happen. Okay. So now can you see it? Yay. Okay. So, and this is a square. Okay. So, so this is a square. So what would it be called? A square what? Pyramid. Thanks, Betty. So this is a square pyramid. And I know it's a pyramid because it has a single base and it has triangular lateral faces and it comes to a point. Unlike a prism that has two identical parallel bases that the lateral faces are rectangles. Yeah? Okay. So now that you know that, we need to find, sorry, I didn't mean to hit that on this screen. We need to find the surface area. So we need a formula for the surface area of a prism. I think I put your formula sheet right here. So when you're looking at these, we want not a prism, we want a pyramid. So it's 1/3. Oh, that's our volume formula. Sorry. It's 2b plus ph, where b is the area of the base, p is the perimeter, and h is the height of the prism. So that's the formula we want to use. Now, we could decompose the shape and find the area of each one of these, right, faces. But our surface area is 2b plus ph. So first we have to find the area of the base. Okay, so the base in this case is a square. And the area of a square, you could say base times height, or you could say a side squared. Doesn't matter. But in this case, it's going to be 16 centimeters times 16 centimeters, just for the area of the base. Do you all agree? Okay, now, the base is 256 square centimeters then. Now, notice that I wrote in centimeters here and centimeters there. You guys probably aren't used to that. Your teachers probably left that off most of the time, or you leave it off when you're writing. But it's very helpful in teaching because it shows students where the square centimeters come from. Because if I multiply something times itself, it is squared. So it's a nice way for students to understand, how did those centimeters now become square centimeters? Well, it's because you multiplied centimeters times centimeters. Okay. So that's the area of the base. So that's going to go right there. Now this P stands for the perimeter of the base. So we want to find the distance all the way around the outside of that. So the perimeter of the base is going to be 4 times 16 centimeters. This is also a nice way for you to see why perimeter is only measured in linear units, right? One-dimensional units, because we're just walking around the outside of this square. So, and we're not multiplying centimeters times centimeters, so it's just going to stay centimeters. Does that make sense to everyone?
Where'd you get the 4? Oh, sorry, my never
Tell
mind.
me
Nope.
where we got the 4. You tell me.
The 4 sides. I'm sorry.
There you go. Yep. No, you did perfect. You could have just put 16 plus 16 plus 16 plus 16, right? I just said, oh, there's 4 of them. Somebody else had that same question, Bethel, and is thankful that you said something out loud. Okay. And the height of this prism is this 24. So I'm going to plug into the surface area formula now. And I'm going to say 2 times 256 centimeters squared plus 64 centimeters times 24 centimeters. And I'm going to do all that math. What? 512 square centimeters plus, yeah, I'm not sure I can do that in my head right now. I could use my estimating techniques or my partial products techniques that we learned in 256. 1,536 centimeters squared. Notice centimeters times centimeters is going to give us square centimeters. So now I can add those two together and I get 1,536 plus 512, and I should get 2,048 square centimeters. Is that what everybody got?
Yes.
Yeah, and you could get that a different way. You could do the triangle formula, right? And you could say, okay, I want to know the area of this triangle, so I need to do 1/2 base times height. But the problem is, do you know this slant height? You don't. You could figure it out, which is what we're going to do in a minute. But just so you know, that's why I think this formula, it's just easier to use your formula sheet. So that's the surface area. Everybody okay with that? Okay. Now, the formula for volume of a pyramid is 1/3 the area of the base times the height, right? That's from this formula sheet right here. 1/3 base times height, where capital B is the area of the base. Well, good news. We already know the area of the base, right? We figured it out because it's the same shape. So the area of the base is this. The height is 24. We didn't need the slant height in this case. Let's look at the formula where we need the slant height, just so you know. This is the formula where we need the slant height. Wait, isn't that what we just did? How come nobody's correcting me on all my issues that I'm having? Anyone notice what we did wrong? Which formula did I circle?
Use the formula for the prism, not the pyramid.
Yeah. So that would be awesome if this was a prism. Too bad it's not. Okay. So we do have to go and use this formula. All right. So we're going to go back. This is so fun. And we're going to go like this. La, 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 la. That formula for volume is right. All right. So my real formula, I wrote that it was a pyramid. I just decided that I didn't need to use the pyramid formula. I decided that I could just substitute the prism formula. You can't do that. So the pyramid formula is B plus 1/2 PL, where B is the area of the base, P is the perimeter of the base. So we did need some of that information. And L is the slant height. Okay, so we're almost there. So capital B, we did figure out, was 16 centimeters times 16 centimeters. So it was 256 square centimeters. The perimeter of the base was 4 times 16 centimeters. So it really was 64 centimeters. Now L is what we need to find, which is this height right here. So notice that if I take my height of 24 and then I draw this line here, I have a right triangle. Yeah. So the height of the pyramid is going to go straight down the top of the pyramid, right down to the center there. So now I can find this length right here, this slant height, by using the Pythagorean theorem. Which is a squared plus b squared equals c squared. So these two would be a and b, and the hypotenuse is L. So what is the value for this length right here? It's 8 because it's half the full base. So you're right. So 8 centimeters, I'm going to square that, plus this length is 24, that height, 24 centimeters squared equals c squared. So now we can do 8 squared, we know, is 64 centimeters squared, plus 24 squared is 576 centimeters squared. So c squared is 640. So I just want c though. I don't want c squared. So I'm going to take the square root of 640 and I'm going to get 25. And if we rounded to the nearest tenth, I would say 3/10. Is everybody with me there? Now I could have an exact square root if I wanted to, right? I could simplify this. This is going way back for some of you. The perfect square in here, this would really simplify to 8 square root 10. Is everybody okay if you follow that? If you don't follow that, that's okay. The square root of 64 is 8. And then there's a 10, right? Because 64 times 10 is 640. Okay, but we'll just approximate it for our life right here. So C is going to be 25 3/10 in our life. Mine will come out perfect on your test. So you don't have to worry about this part or even approximating. It'll come out nice for you. Okay, so now we're going to go back to our formula and plug in. B, which is 256 centimeters squared. This is our surface area. Plus 1/2 times the perimeter, which is 64 centimeters, times our height, our slant height, which is 25.3 centimeters. Now I will get half of 64 is 32. right? So I can just multiply 32 times 25.3, and I get 809 and 6/10 square centimeters. Please check my math. Obviously, I'm having some sort of issue today since I used the wrong formula. 1,065 and 6/10 square centimeters. Is that what you guys got? Anyone confirm, deny?
That's what I got.
Yay. Okay. So yeah, it helps if you use the right formula. Please pay attention to that. That was my note of what not to do. Now let's find the volume of this. The volume, I had the right formula. That's when I noticed I had the wrong formula for the surface area. So the volume of a pyramid is equal to 1/3 base times height. So we already know the area of the base is 256 square centimeters. We're going to leave the 1/3 in the formula, and the height is 24 centimeters. So volume's actually much easier than surface area, right, to compute. Now, I like when you write it all out so you can see it, because notice now that you're multiplying square centimeters times centimeters. So now you have cubic centimeters. That's why it's important to put it in the formula. So students see, oh, if I have something squared times the same thing again, it's going to end up being cubed. The other thing that you really are capable of, by the way, you can do this without your calculator. You can say 3 goes into 24 8 times. So now I can just multiply 256 by 8. Yeah. Does everybody see what I did? You'll get the same answer if you do it on your calculator or if you do it just by hand. You should get 2,048 centimeters cubed. Yes? Everybody okay? And there's at least one on your final, on your Canvas portion, where you have to find that slant height. Okay. So make sure you know how to do that with the Pythagorean theorem. All right. Any questions on that one?
What formulas we will need to remember for sure? Are what again?
You need to know all the area formulas. You need to know perimeter, circumference, Euler's theorem, and interior angles.
Okay.
And it should all say that on the review sheet. I hope. All right. So, anybody still need this slide to look at? Anybody still looking at this? You okay?
It'll stay in your OneNote, right?
What? Yeah, it'll stay in
Okay.
OneNote. Yeah, absolutely. Okay. Before we dive in to transformational geometry, it's our last We Share Wednesday. I know. Are you freaking out? No, you're freaking out for other reasons, but that's okay. How about anybody have anything to share? This is the last time we'll be together.
I can share one thing.
I'm ready.
I am going to Albuquerque this Friday. I'm gonna spend the weekend over there. We're gonna go, a family friend of ours, her daughter's graduating high school, and so we're gonna go over there and see her graduate.
Nice. That sounds fun. And they're doing in person and they're letting lots of people come. That's interesting.
New Mexico is different over there, I guess.
I guess. Well, be safe, right? Good. Who else has something fun to share? That's super exciting. I love graduations.
I have something.
Yeah.
My brother's graduating high school this year, and
we weren't sure what was going to be happening, but they just opened it up so 4 people can go, so I can go see him graduate with my parents.
Yay! That's nice. I think it's nice that they're having graduations, and it's nice. It's especially nice if they're limiting the numbers just so it doesn't get too crazy, right? Yeah. I have about one graduating from college and one graduating from high school. So, but they're both in person. So my son's who's graduating from college, you can only bring 2. So, which is fine. It's just me and my husband. So, you know, I mean, we have relatives in Omaha, but we'll just see them after.
We won't be having class next week.
Nope, we just have our oral finals. I'm giving oral finals literally 24 hours a day, I think, for 3 days. Maybe not that bad, but a lot.
Will you be having office hours next week or no?
Nope.
Yeah.
Nope. So if you need me, you just need to let me know. I have office hours tonight. Yay. Finals week, I never have the same office hours because it's always crazy. I have finals. Let me see. Let me look at my schedule. Monday and Tuesday I have finals starting at 7 a.m. So yay me. I love that, Tyler. Last day of classes and exams with MCC, then headed to Hawaii for a week starting tomorrow. That's awesome. All right, anyone else? Okay, transformational geometry. That's where we're going to have geometry now in motion. So we're going to talk about translations, rotations, reflections, and dilations. And you have Desmos activities for all of those that you can do all on your own. What we're going to focus on today is what on earth those are, how we do them, and we're going to start. Oh, Sunita, yes, an A on your chemistry lab. That's awesome. Your lab exam. That's cool. We are going to start on your worksheets that you have. Okay, so you have worksheets that are all together, translations, rotations, reflections. We're going to do at least one problem on each one of those. If we have enough time, I'll put you guys in your breakout rooms and you can work on the rest of those. I just figured it's better to do the worksheet one because the Desmos one you can do, you know, on your own whenever you want. So in case you don't have this worksheet, I'm going to put it in the chat. It is in OneNote. Hold on. Oh, and just in case you're not looking at it, there is a transformation foldable that is probably one of the most amazing foldables I have ever seen. It can be used for so many different things, and it is on Teachers Pay Teachers, and I never pay money for anything on Teachers Pay Teachers except this. This, not what I just put in the chat, but this transformation foldable. It is $5 and it is worth every cent. So I highly recommend you buy it and then replicate it for other subjects as well. I thought I had my finished one just sitting here. So anyway, check that out. I also have a picture of the finished product, but it is way cool. It's probably one of my favorites ever. So you don't need that worksheet right this second, but we're going to get to it in just a minute. There's 4 types of transformations: translations, rotations, reflections, and dilations. Translations are considered slides. Rotations are turns, reflections are flips, and then dilations are enlarging or shrinking. And you can see examples of these in your real lives, right? Like a slide at a playground translates you from the top to the bottom. You don't change. You're still the same person. You're just in a new location. A rotation, if you stand up and turn around in a circle, you've rotated 360 degrees. Again, you haven't changed. You just turned around. A reflection, every time you look in the mirror, you see a reflection, right? So that's an example in real life. And then dilation. Has anyone gone to the eye doctor and gotten their eyes dilated? Yeah, what happens there? They don't make your eyes bigger, but they do something. What does it do? Anyone know?
It makes your pupils bigger so they can
Ve-
see the back of your eye.
Very nice. It makes your pupil get larger so then they can see all the way into your eye better. So a dilation actually changes the size. All the other ones don't change the size. Okay. There's a video that's in this if you want. And then like I talked about the foldable. So when you do a transformation, no matter if it's a translation, rotation, reflection, or dilation, we change the lettering of our vertices. If in the original it was just A, in our transformed image, it will be A prime. So A with a little tick mark. Make sure you label them that way, right? If you're doing something or if you're giving me an example of something. Sorry, like on your oral exam, if you're giving me an example of some kind of transformation, make sure you show me that tick mark. So a translation is a slide. It moves an object in a fixed distance in a given direction. Again, it's the same size and shape. So for example, right here, this parallelogram moved over. It didn't move up or down. It just moved over. Okay, so that's a slide. Here's an example. So if we have this original triangle, I know this is my original triangle because my vertices do not have tick marks. Okay. So I have triangle ABC and it's shifted or translated 6 units to the right. Okay. So each vertex moved 6 units to the right and then we connected them again. So notice that the triangles are still congruent. It's the same triangle. It's just in a new location. Okay. Everybody all right with that? So we could look at our coordinates. So if we have A was a -4, 5, B was -1, 1, and C was a -4, 1. Now, this is what you might be noticing. A prime is 2, 5. Well, if I take -4, 5, and I translate it using, I say, okay, my X coordinate, this is my translation. My X increases by 6, which means it's sliding 6 to the right, but my Y doesn't change at all. That's how I could write it algebraically, how I want to describe what's happening to this. So my X is moving 6 spaces to the right, my Y is not moving at all. So if I do that, if I take this -4 and I plug it in right here, -4 plus 6 would give me a +2, and then my Y didn't change, so my new coordinates are 2, 5. So I don't have to just do it in a picture. I could do it algebraically. Does that make sense? And you could see how B prime and C prime are as well. Okay, here's another one. This one's moving 7 units left because this is my original shape. I know that because my vertices do not have tick marks on them. And so my translated shape is 7 units to the left and 3 units down. You could say 3 units down and 7 units to the left, but since algebraically we usually list the X coordinate first, we would say X minus 7, comma, Y minus 3. Now tell me why the subtraction. Why is it subtraction?
Is it because you're going to the left? And
Correct.
left it's negative?
Yep. So on this number line or coordinate plane, you can see when I move in this direction to the left, I'm moving down. So I'm subtracting, right? And when I'm going down on the vertical axis, that would also be going down. So I'm subtracting. So you could take one of these coordinates, like this one right here. What are the coordinates of point A?
Two, 4.
Very nice. 2, 4. If I plug that into this translation, I can say 2 minus 7, 4 minus 3. And so A prime must be negative 5, 1. And if you look at your graph, that's exactly where A prime is. Negative 5, 1. Make sense? So you can translate it with coordinates, or you could translate it like this. You could go, okay, 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 3. And you'd still end up at the same point. So you can do it visually or algebraically. Everybody okay so far? Nice. And I have all these coordinates now. You can see them. So this is the first problem on your translation worksheet, the one I put in the chat. So if we want to go 5 units right and 1 unit up, somebody, actually all of you, type into the chat how you would describe that algebraically. What would it be for X and Y? How would I describe this translation algebraically? Get it ready in the chat. Everybody have it ready? It's okay if you're wrong. Bethel, don't make that face. We can be wrong. It's good to be wrong right now, right? Because then we'll all learn something. Okay, 3, 2, 1, go. Okay, let's take a look. People wrote X plus 5 and Y plus 1. It's plus because we're going to the right, yeah? And we're going up. Now, one could be, we could go to the right and down, right? So one could be a plus, one could be a minus. Now, let's do this translation. You can do it by algebra. So you could say, okay, the original coordinates of G are -1, -2, -3, -1. So the original coordinates are -3, -1. My translated coordinates for G prime, I would do -3 plus 5 and -1 plus 1. So my new coordinates would be 2, 0. So I'm going to plot that 1, 2, 0, and I'm going to say that's G prime. I could have counted it. I could have said, okay, I'm going 1, 2, 3, 4, 5, and 1 unit up. Either way, I would still get right here. Try it for T and B, and let's see if we all did it correctly. Is that where yours was? Was T prime at 1, 2, 3, 4, 0? And B prime was at 2, -4? Any questions on that? You feel pretty confident in translations? They're not bad. I don't think translations are bad. So now if you notice on that worksheet, the first page has you just do translations like we just did. But then the second page asks you to describe the translation. So when you describe the translation, make sure you're looking at the pre-image, the original image, and then the transformed image, and write it in words and write it in algebra because it's great practice. Okay. All right. let's look at rotations next. I'm going to give you about a minute to digest that. Don't try to do the rest of the problems right now, because then you'll miss rotations and you'll be crying. All right. So a rotation is just what it sounds like. It's a turn, right? And it's about a fixed point, and that's the center of rotation. All the rotations I ask you to do will be about the origin. Okay, so if I ask you, and it's going to be about the origin, like on this paper. And you can see this all over the place. You can see it in wallpaper designs, fabric, artwork, everything. So here's a rotation, and it's 90 degrees counterclockwise. Now, counterclockwise is the default. So if it doesn't say which way to rotate it, it wants you to rotate it counterclockwise. Anyone have a reason why counterclockwise would be the default? Any ideas? Doesn't seem very intuitive.
Isn't that like how the sections on the coordinate graph go?
Yeah. So the quadrants go, if we look at back at our coordinates, so the quadrants, this is quadrant 1. So this is 1, this is 2, this is 3, and this is 4. So it would make sense for the default to be counterclockwise. Okay. By the way, I don't know if I ever told you the story. My son in 3rd grade came home and was doing a math project that was all about plotting points on a coordinate plane, and it was like sinking a ship. It was a really cute activity. And he came and he never asked me questions on his homework. And he came to me and he said, "This homework assignment doesn't work." And so I said, "Well, let's take a look." And he was explaining it to me. And he had his quadrants labeled this. He had it labeled like this. Maybe he had it like this. I think he started in 1. So 1 was correct. So this was 1, this was 2, this was 3, and this was 4. And that is incorrect, right? Because I just told you it goes counterclockwise. So I said, your quadrants are labeled incorrectly. It goes counterclockwise. And I relabeled it. And I tried to say, I said, go try the activity now. He said, nope, you're wrong. My teacher told me that it's 1, 2, 3, 4, clockwise. And I said, well, math hasn't changed in a really long time, right? Do what you want, write on the problem. It doesn't work, but I'm telling you, it's 1, 2, 3, 4. He threw a huge conniption fit. Like, it was insane. So I said, so after about 10 minutes, I called the teacher. And I said, hey, she was a brand new teacher, 1st year teacher. I said, I just want to let you know, my son's struggling a little bit. He has his quadrants labeled clockwise from top right, 1, 2, 3, 4. And the quadrants go counterclockwise, 1, 2, 3, 4. And she goes, oh, I taught them all wrong. And I was like, yeah, that's kind of why I'm calling you, but I didn't say that, right? And I said, I just wanted to make sure it was okay, and she's like, no, tell him he doesn't have to do it. No other parent has called me. He doesn't have to do it. Don't worry about it. And I'm like, okay. So I told Mace, my son, he's like, you're wrong. My teacher's right. I don't know. You don't know what you're talking about. So the next day I happened to be at school volunteering, and the teacher came up to me and she's like, oh my gosh, I'm so embarrassed that I taught them all wrong. I had to reteach the whole lesson. And I'm like, that's okay. And I said, did Mace believe you? My son. And she's like, oh, he had it done correctly when he came in. He had changed the quadrants to counterclockwise. And I was like, ah. So anyway, apparently, even if you're a math teacher, you don't know what's going on. So keep that in mind if any of you have your own children when you're teaching, because you will not be able to convince them that their teacher was incorrect. So, which I guess is a good thing. I don't know. Okay. So rotations are hard for students, okay? Rotations are hard for students. And let me explain to you why they can be so challenging. It says I want you to rotate this 90 degrees counterclockwise about the origin. So picture this. I have this on actual paper, by the way. Or I thought I did. Rotation, rotation. Okay, here it is. So I have this on actual paper. So picture, you don't have to see what's on the paper. I'm just explaining it to you. So if you have your paper in your hand, if you want to rotate it 90 degrees counterclockwise, you would turn it like this. Yes? You have it in your hand. You would turn it like this. Okay. So that's exactly what it's telling you to do. And then it's telling you to record all of that information. So that can be hard for our brains to understand. And Desmos is going to help you see some patterns with that, but I want to do it kind of low tech. So right now, let's just write down all of these coordinates. So B is -4, 1. X is -3, -2. And N is -5, -4. Is that right? Did I get those right? 5, 1, 2, 3, 4. Okay. And I want to rotate this 90 degrees counterclockwise. So another way to do this activity that kids really like, have any of you ever heard of patty paper? Patty. Looks like this. Okay, patty paper. I'll take out a piece. This has 1,000 sheets in it. I don't know, it was maybe 20 bucks at the most. It will last you forever. See it? It's just a little piece. Anyone do scrapbooking or anything with paper? It's like the little piece that comes in graduation announcements, or like vellum would even work like that. So that's what it is. So if you take this and you put it on top of your paper, you can trace your original shape, right? And make a little X on your coordinates. And then you can just turn the paper 90 degrees and know exactly where it goes. This is an outstanding tool if someone is struggling with this idea. So, and by the way, in a pinch, you can go to your lunchroom at school and they have little pieces of paper like this that they put in there, like they're like lunch boats. So I've been known to go to the cafeteria and borrow some. Borrow might not be the right word because I'm never giving them back. Okay. Just like when you make gingerbread houses at Christmas in kindergarten, you just go use all those little lunch boats, right? And you build the gingerbread houses inside there so all the stuff doesn't fall all over the place. So just tricks of the trade, right? Okay. Or in a pinch at your house, like if you're doing this activity and you printed it out and you're struggling, just get wax paper. Okay, wax paper will work for you in a pinch. It's a little harder to see. Okay, so now if you can imagine turning your head, if I turn my iPad, the whole thing's going to rotate, I think, so it won't matter. But if you can imagine the new coordinates, if I turned it this way, 90 degrees, counterclockwise, B prime would be -1, -4, -1, -4. Can anyone see how I would get B prime? Would be -1, -4. So it would be right here. 90 degrees counterclockwise. Everybody okay? Okay. X prime would be 2, -3. 2, -3. And then n prime would be 4, -5. Now, some of you might be noticing what's happening to our coordinates. So let's do 2, -3, 1, 2, 3. So this is x prime, and 4, -5. That would be n prime. And then I'm going to connect these. This new shape will be congruent to my old shape. Okay. How many of you knew that's where it would be if you rotated it 90 degrees counterclockwise? I love Brianna, Bethel, Maddie. They're all like, I got nothing. I still don't know why it's there, right? Doesn't make any sense to me at all. If you take a little piece of paper, if you're only doing it electronically and you're spatially challenged, like me, it's hard. But if you have it seriously, like turn your head sideways, this can sound really dumb. Turn your head sideways and you'll see what's happening. Or if you have an iPad, you might be able to lock your screen, right? And if you turn it just a little bit, then you'll see those coordinates. But if you notice, let's compare these coordinates here. What do you notice about my X and Y?
They flipped.
Yeah, what do you mean flipped? Now my Y is my X, yes? Did anything else change? Something else changed.
The integers,
What do you mean?
like in B, it was +1. Now in the new coordinates is -1. But
Yes.
you still have -4, which
So the X didn't change. It still stayed X. It just moved into the Y category, right? Just moved into the second coordinate. What happened to the Y? How would I say it changed signs? What would I put there?
A negative sign.
Yeah, I would put a negative sign in front of it to say, take the opposite of it. Yeah. And did that work for all of those? Yeah, look, the -3 still stayed -3. It just moved to the Y position, and my -2 became +2. In the last one, my -5 was still -5, and my -4 became +4. So that only works for 90 degrees counterclockwise. Yeah. So unless you want to memorize all these things, you're going to have to actually try to visualize or use some patty paper or some tracing paper or something like that. Okay. So the rotations are kind of hard. Yeah. Michaela's like, yeah, I'm dead over here. Got nothing. These are hard. Okay. Look, we were right. See? We really did. Oh, and that was number 3 on your worksheet, apparently. Okay. A reflection. A reflection, you guys know what it is. If I cut things down the middle, those two halves look like each other, right? So this is the line of reflection, right? So if I have this as my line of reflection, here's what you should notice. If I folded it along this line, this A, B, C, D quadrilateral and the A prime, B prime, C prime, D prime quadrilateral would be right on top of each other. Yeah, if I folded it. So these are not called rotations or turns, they're called flips because the image is inverted, right? So what you should notice is that B and B prime are the exact same distance from the line of reflection. Okay. So each vertice is the exact same distance from the line of reflection, just on the other side. That's a perfectly straight line, in case you're wondering. Okay. So I think reflections are a little bit easier. I did say a little bit. Okay. So look at this reflection. So here's, which one is my original? Is it the one in quadrant 1 or quadrant 4? Yeah, Betty's like 4. I got it. I look for the tick marks now. So this is my original. Okay, this one down here is my original. Now, I could list all these coordinates, right? A is 2, -3, B is 5, -4, C is 2, -4. What is the line of reflection in this case? So you can see it's flipped over a line, right? It's flipped over some horizontal line. Can you tell which horizontal line?
The x-axis?
You got it right here. And you know that because if you look, A is 1, 2, 3 units from there. A prime is 1, 2, 3 units from there. So my translated image, sorry, my transformed image, my reflected image is 3 units above the line of reflection, whereas my original image is 3 units below. So you can literally just count. So from here, I would go, okay, 1, 1, I don't know why it won't let me draw. Oh, 1, 2, 3, 4. And then I'd go 1, 2, 3, 4. And I'd put B prime there. Same with C prime. Doesn't reflection seem easier? Yeah, till you forget what lines are. And we'll talk about that in just a minute. Okay, so let's look at this one. This is the first problem on your reflections worksheet. So it says reflect across y equals -2. What kind of line is y equals -2? What do you think?
It's the second. It is the second y-axis left of the origin. Because it's a
So
negative.
which way do you want me to go from this point right here? Which way do you want me to go?
That way.
You want me to go left? Okay. That's where you want me to go?
Yeah.
Everybody agree with Helena? Betty said left. Brianna said down. Essay said down. So from this point, you want me to go down to some of you. Which way should I draw my line, horizontal or vertical?
It should be vertical.
So some of you think it should go right here, yes? And some of you think it should go right here, am I right? That's the argument. Is it a vertical line or is it a horizontal line? I want you to think about this. It's saying y is -2, yeah? Y is -2. So what are the coordinates of that point right there? What's the coordinates of that point right there? Somebody tell me.
-2, 0.
Yeah, -2, 0. Thank you, Essay. Essay's like, why is nobody answering? -2, 0. Now, what are the coordinates of this point right here?
0, -2?
0, -2. So in which one of these do I have -2 as my y value?
The second one.
Yeah, the horizontal line. Yeah. So now that we've figured that out, the line of reflection is a horizontal line right there. That is the line y equals -2. Some of you are like, okay, fine, I feel better now. I was right. So that horizontal line is y equals -2. It's not intuitive. If it says x equals -2, that is a vertical line. But I want you to think of all these coordinates of all these points. No matter what x value it is, right? No matter how far right or left, we're always down 2. That means our y value is always -2. So good job, those of you who were brave and saying, I'm not sure I agree. This is a hard thing. It's confusing. People mess this up all the time. So if it said x equals a number, it would be a vertical line. When it says y equals a number, it's a horizontal line. That might be backwards in your brain. So be careful with that. Okay, so now that we know our line of reflection is y equals -2, and it looks like this, a horizontal line at -2. Now we can plot all of our transformed coordinates. Well, here, this one's nice. This one's on the line of reflection. So that is I and it's I prime, both. It didn't move. Okay. Now, E is 1 unit below the line of reflection. So E prime is going to be 1 unit above the line of reflection. I think that's an X. I feel like that's an X. No, I think it's a Z. 1, 2, 3, 4, 5. No, wait. 1, 2, 3. So I'm going to go up 1, 2, 3. And I'm going to label that Z prime. I'm pretty sure it's a Z. And then Q is 2 units below. 1, 2. So I'm going to go 1, 2. And put Q right here. Q prime. So now I'm going to connect these. Now, my shape should look exactly congruent, just flipped over. Yeah? Everybody okay? It's congruent, it's just flipped over. Everybody all right with that? Okay. There's my nice one, and it was a Z. I feel so much better. Okay, the last one is a dilation. Here's the good news. You don't have any worksheets on dilations, and the dilation activity on Canvas is optional. What that means is I didn't put that on your final. Okay, dilations aren't on your final, just translations, rotations, and reflections. Okay. So don't worry about the dilation desmos. If you want to do it, you can, but you don't have to. So a dilation just makes it larger. So you can see each one of these coordinates has been multiplied by a scale factor of 2. So for example, A was at -2, -2. Now it's at -4, -4. I just multiplied my X and my Y by 2. Or you could shrink it, right? So that's what dilations do. And there's a little more examples and then just some review. So what I want to do now for these last 15 minutes is I'm going to put you in breakout rooms to do these worksheets, okay? So you can get them done and ask me questions maybe even, okay? So now when you do, some of you might get stuck when it says, what if it says the line is y equals x? What does that line look like? A line that says y equals x or x equals y. What kind of line is that?
It's diagonal through the X and Y axis.
Very nice. It means that all your coordinates are equal. So it goes through the point 1, 1, 2, 2, 3, 3, right? So it looks like this. So that's y equals x. What about y equals -x? What does that one look like?
It's the opposite. It goes from the left to the bottom right, top left to the
Nice.
bottom right.
Nice. It goes this way. Those are the only kind of lines besides just horizontal and vertical we have. Okay. All right. So I'm going to put you in your breakout rooms in just 1 minute. I'm just making sure everybody's somewhere I can find them. Okay. And call me in your room if you want help. All right. I'll see you in a few. Hi guys, were you wondering if you were ever coming back? Sorry, I forgot to push the button. that said close your rooms, but we're back now. So, and time's up, class is over. Can you believe it? I know. I talked too much. You guys didn't get to do enough work. It's okay. I hope you tried to do the harder ones first instead of doing the easier ones first. That's a good plan. If you need help with this, remember I have office hours this evening. Your exit ticket is right there. Let me put it in the chat. I think once you get the hang of it after the Desmos practice, you'll definitely know what's going on. So you don't feel like you have to have all the Desmos activities done before like you do something else. Like if you have your final with me today, you'll be fine once you have an idea of what's happening. I'm sure you've prepped your questions already, but let's say I think those are all due, are they due Friday? Are those assignments due Friday? So if you need help tonight, I can help you. Otherwise, I think if you go through them, you'll be fine. And you're just getting points for completing them. So if you make an effort, even if you might have a couple mistakes, you should be okay. All right. Okay. Well, I can't believe this is our last meeting. I wish we could meet in person, like live. I'd love to see your real faces. I think you guys would be shocked at how short I am. I'm just saying. So, okay, have a great weekend. And I will see every single one of you in your oral final exam, except for Hannah. Hannah is the one I did already. So bye, Hannah. But you can come visit me in office hours if you want to. We can have lots of fun. All right, have a good day. When your exit ticket's done, you can go. Bye. See you later.
I have a question about the Desmos activities.
I'm ready.
There is no button to submit the assignment. How will you know when we're done?
I can see, as soon as you start it, I can see exactly where you are. It records everything.
Okay.
The only thing that's a pain, Elena, is if you don't finish in one sitting, it won't save your work unless you're signed into your Maricopa or to a Google account. So if you're afraid you're not going to have time to finish, it would be wise to sign in, because then if you stop, when you come back, it'll just pick up where you left off. Otherwise, you'll have to start back over.
Okay.
There's nothing to submit. So I'll just check it. And then I just look, there's like, I can go through each person's every single slide, and then I can grade it.
Roxanne, I had a quick question about the rotation of 180 degrees.
Yes, I'm ready.
We were starting on that, and I just wanted to make sure my thinking process was right.
Okay, I'm ready. What's your thinking process?
So instead of the because you said there was like a way to remember it, like the 90, like how we did the 90 degrees where you just write like, you know, negative y and then x or something like that. I don't know, something like that.
Yeah.
But my theory, if I didn't remember that, I would just move the coordinates to quadrants, and so like, because that's 180 degrees, right?
You could do that. Yep.
And then just follow along like whatever like if it ended up in the, so let's say like, okay, I'll show you my example, like this one.
Yes.
Like we point P, if we rotated at 180, it would end up in the third quadrant.
Yeah, so what would the coordinates of it be?
It would be -1. Oh wait, yeah, -1, -4. So
okay, now pause for a second. That totally works. No worries. But I want you to look now at the coordinates of P were 1, 4, and the coordinates of P prime were -1, -4. Can you see a relationship there?
Mm-hmm. You just flip the integers. It's like the opposite. I mean, it's, yeah.
Find the opposite. Yep.
Okay.
Each one of them.
And then then 270, I was thinking that it would have the same kind of relation to like a 90-degree rotation where you flip the y and x, right? the X and Y would flip. I mean, change spots, and then just the, was it the X? I think it's Y that'll be changed now?
Yep.
Okay.
It depends on which way we're turning it, right? Because a 270-degree rotation clockwise is the same as a 90-degree counterclockwise.
That's true.
I know.
So if it says about the origin, are we just assuming that it's counter? Oh yeah, you said that's counterclockwise, but if it said clockwise, like 90 degrees clockwise, we would be
Okay,
going.
now what's interesting is why doesn't it have to specify when it says 180 degrees? Why doesn't
Because
it
no
have to
matter
say
what,
clockwise or counter?
you'll end up going the same in the same quadrant
Yep,
essentially.
you'll end up in the same spot, whether you turned clockwise or counterclockwise.
Or
So
counterclockwise.
if I had you stand up and said turn 180 degrees, it wouldn't matter if you turned
That's
to your
true.
right or turned to your left, you would still end up with your back to me.
That is true. Okay, but that's why it's I mean, are there, I don't know, but like, are you gonna specify like, I mean, if it were 90 degrees counterclock, like, are you gonna
If
say
it's
that?
90 degrees counterclockwise, I will tell you counterclockwise or clockwise.
Okay,
If
okay,
it's 180, it won't specify.
okay, or oh wait, I guess 270.
270, it'll specify.
Okay,
Yep.
sounds good. I was just making sure I mean, like, because I like doing the quadrants better.
That is an awesome.
Because that makes sense to me. So yeah, we were figuring that out in our breakout room. So yay. Okay. I think I got the other reflections and translations are okay though.
Yeah, I think rotations are the hardest.
Mm-hmm. Just because you can't like picture it in your brain, you have to actually like, I don't know. It's not making sense. Like if I just look at it, oh, like rotate it.
Yeah, I agree. I agree.
Yeah, so thank you. I'll see you. So we don't have class tomorrow.
No class tomorrow.
So I literally thought we had class